Okay, we move on to the third part of kinematics. Okay, we are still under how do we analyze motion graphically. Okay, in the first part of how do we analyze motion graphically, we talk about how do we interpret a displacement time graph and velocity time graph specifically into the gradient. Okay, what does the slope of the graph represents? Okay, but there is another useful information for a velocity time graph. Okay, you need to know that the area under a velocity time graph actually gives you the displacement of the object. Okay, so every time when the question asks for distance or displacement, okay, it's good to know that it's not only distance or displacement is not only speed times time, it's actually area under a velocity time graph. So every time when the questions have distance or displacement, you need to sketch out the shape of a velocity time graph and find the area under it. And what do I mean by area under the graph? It simply means the area between the line that you draw on the graph and the x-axis. So if my line is over here, then the area under my graph is between the line and the x-axis. This entire shaded yellow portion will be the area under the graph. Okay, let's take a look at a little bit more examples. And I hope you know the formula for a trapezium. You should be able to recognize what's a trapezium and also how to find the area of a trapezium. So let's take a look at the following velocity time graph of this object. Okay, so how do I interpret it? Again, the gradient of a velocity time graph gives you the acceleration. So in this graph, it's all straight line. So I use the word constant. So at the first part, I have a constant acceleration. Second part, I have a zero acceleration, means not accelerating. I'm moving at a constant velocity. And the last section, I have again a constant, no longer accelerating. My object is decelerating. So I have a constant deceleration. Okay. And at the bottom here, you can see how do I calculate that acceleration. So acceleration is final velocity V. Okay. The final velocity over here is 36. Minus the initial velocity, 0, over the entire time of 6 seconds. So 36 divided by 6, you get 6 meters per second squared. At the second portion, acceleration will be 0. Okay, I'm moving at a constant velocity of 36. At the last section, okay, again, how do I find acceleration? V minus U over T. My final velocity will be 0. My initial velocity will be 36. So you can see it's 0 minus 36 over the timing of 24 minus 15. Okay, 24 minus 15. Okay, because it's from 15 to 24 seconds. So I should be able to get an acceleration of minus 4, which means that it is decelerating at 4 meters per second square. Okay, then I want to calculate the average speed or average velocity of this object. So the average velocity, you need to think back, or average speed or average velocity, think back into the formula is the total distance or total displacement over total time taken. So total distance or total displacement, I need to find the area under the graph. So my graph line is the red line. The area under the graph will be between the red line and the x-axis. So it will be this entire shaded blue area. Okay, throughout the whole journey. And the total time taken will be 24 seconds. So how do I find this shaded area? You can obviously find a triangle, square, triangle. But you should know mathematically that this is a trapezium and there is a formula for the trapezium. Okay, area of a trapezium, which is given by the one in brown over here. So the area of a trapezium is given as half times the sum of the parallel sides. The parallel sides will be from 6 to 15, which is 9 over here. 6 to 15, 9, plus sum of the parallel sides. So it's 9 plus 24. Okay, this and this is my parallel side. So it's 9 plus 24. Half times 9 plus 24 times the height of the trapezium. The height of the trapezium is over here, which is actually 36. So you get 0.5 half times 9 plus 24 times 36. You should be able to get 594 meters. So this will be the total displacement covered. And I want to find the average velocity or average speed will be total displacement over total time. So it will be 594 over the total time 24. I should be able to get 24.8 meters per second. Okay, so I give you more example. Okay, if the graph is like this, then I will say that my area under the graph will be 0. My displacement will be 0. The object doesn't move at all. Okay, and if my graph is this line, red line over here, then the displacement will be the area under this graph. Between this line and the x-axis will be this shaded triangle. It will be, B first. Okay, it's again a straight line. So the area under the graph will be between the line and the x-axis will be this rectangle. So it will be 10 times 5. Okay, and for C, it will be half times area of triangle, half times 50 times 5. Okay, and lastly for D, if my line is like that, it's again between my line and the x-axis. So it will be this green shaded area. Okay, it will be again half times 50 times 5, 125 meters. Okay, then let's take a look at more examples. Okay, I have a ball. I am throwing the ball upwards. Yeah, I'm throwing the ball upwards. Okay, so the ball will reach the highest point and then it will drop back down. Okay, so how does the speed time graph how would the speed time graph compare to the velocity time graph looks like? Okay, just take note, I always have students who thinks that the ball is going up means the graph must be going up. It's not in this case. It's not a pictorial form of the motion of the graph. Okay, you need to think a little bit. Okay, when my ball is throwing up and my ball is moving up, gravity is pulling the ball down. Okay, my ball speed or velocity will decrease. It will slow down. The ball will not get faster and faster and faster as you throw it up. If it gets faster and faster and faster, then your ball will never stop moving. It will continue to move upwards. It will never come to a stop. Okay, so actually because of gravity is pulling it down, the speed or the velocity slows down when it's going up. Okay, so let's go into the speed time graph first. Okay, you can see that the speed will drop. Okay, the velocity will also drop. Okay, then after that, you need to know the next most important thing is when it reached the highest point over here at T1. Okay, when my ball reached the highest point, it will have an instant where it stops. At that instant, instantaneous speed is 0 before I drop down. Okay, the speed will be the 0, but the speed will be 0 at the highest point. Okay, so the speed will drop until 0. So T1 over here is the highest point. Same for velocity time graph. T1 will be the highest point. The difference between speed and velocity is that speed is a scalar. There's no negative speed. So you cannot have anything under the graph for speed time graph. But velocity is a vector. There is positive and negative. And remember, I say, once I go into the negative region, it simply means it's moving in the opposite direction. So for speed time graph, okay, there is no negative. Okay, let's zoom into speed time graph first. So now I'm at the highest point. I'm going to drop down. As I drop down, gravity is also pulling it down. So the speed will increase because of this gravity pulling it down. Okay, so when the speed increases, okay, it will go like this. The speed increases from 0 to whatever speed. Okay, that's for speed time graph. I don't care about the direction that I move. Okay, I just only care about the values. The values of the speed decreases until you reach the highest point where the speed is 0, and then it increases again until you reach the floor. Okay, but for velocity time graph, direction matters. The first part is when my ball is moving up. Okay, so I'm at the positive direction as moving up. But then after time t is, after at time t1 where my velocity becomes 0, I start to move down. When I move down, I'm moving in the opposite direction. So now my graph will goes to the negative region because I'm moving down. Okay, and then as I move down, my velocity increases. So it increases from 0 to again a u over here. Okay, the negative just simply tells you it's moving in the opposite direction. So this is the difference between a speed time graph and velocity time graph. There is negative portion for velocity time graph, but no negative portion for a speed time graph. Okay, then after that, let's look at the area under the graph. So the total distance is the area under a speed time graph. So the area under speed time graph, so your graph line is the red line. Over here is a V shape. So the area under the graph is defined as between the red line and the x-axis. So you have area A1 and area A2. So A1 is all the way under T1, where I reach the highest point. So this is the distance that I cover when I'm moving upwards, all the way until I reach my highest point at T1. And then area A2 is the distance traveled when I'm going down. Okay, when I drop down all the way from the highest point to the floor, my speed increases. Okay, until I drop to the floor, where my speed becomes 0 at the instant again. Okay, so the total distance that I travel will be area 1 plus area 2. These two shaded areas add together. Okay, but for displacement, I look at velocity time graph. Okay, so for displacement, again, is the area under velocity time graph. So my red color line is here. For the first part, when I'm moving upwards, I take my velocity as positive. Okay, so this will be the area under the graph between the red line and the x-axis. So this area A3 is the displacement that it moves when the ball is moving upwards. And then after T1, I change direction. I drop down. So I go to a negative portion. So again, my area under the graph is between the line, the red line, and the x-axis. So it will be this area, area 4. And this will be the displacement move when I'm going down. And this displacement will be negative because it's under the negative portion of the graph. So my entire displacement will be A3 plus A4, whereby A4 is negative. Okay, so my displacement will actually be 0 because these two areas are the same. A3 minus A4 away. So my displacement will be 0. I stuck at my hand, I throw the ball up, it moves up to my highest point, and then it comes down back to my hand again. So the total displacement will be 0. Okay, let's take a look at more examples. You may pause the video at this instant to think about the answers. I'm going to go through the answers now. A MRT train moved off from Aljunied Station and traveled along a straight track towards Paya Lebar Station. Then this diagram shows the velocity time graph for that MRT train. Determine the average speed of the train between 0 and 70 seconds. Okay, so the first step I need to think of is the region from 0 to 70 seconds. The entire graph gives me all the way up to 90 seconds, but I don't need to care from 70 to 90 seconds. And my question asks for the average speed. So give me the formula for average speed first. You should be able to get that average speed is total distance over total time. So how am I supposed to get the total distance? The total distance, I don't care about all the way from 70 to 90. I only care about from 0 to 70. So if you are able to get it, okay, the area under the graph from 0 to 70 will be this entire shaded area. Okay, between the line and the x-axis, which is again a trapezium. Okay, so give me the formula, total distance over total time. The total distance is actually half times sum of parallel sides, which is 10 plus, 60, which is 70 minus 10, 60 plus 70 times the height 10. Okay, half times 60 plus 70 times, the height is 15 times 15. Okay, 975 meters. That's the total distance. And the total time it takes is 70 seconds, not 90 seconds, 70 seconds. So this will be my average speed, 13.9 meters per second. Okay, next one, part B. Describe the motion of the train. Okay, they have already helped you segment out from 0 to 10 seconds is one motion, 10 to 70 is one motion, and 70 to 90 is another motion. So whenever I want to describe, please think of the gradient. What does the gradient of velocity time graph gives you? It gives you the acceleration. So the first part, straight line, so I need to see the word constant acceleration. Second part, 10 to 70, again a straight line, but it's a flat line, so it's zero acceleration. It's a constant velocity of 15. And the last part is no longer a straight line. This is decreasing gradient. So I'm having a decreasing, not acceleration, because my velocity dropped. So I'm having a decreasing deceleration. So repeat, first part, constant acceleration, zero acceleration, moving with constant velocity. And the last part is decreasing and it's deceleration because it's negative gradient. Next question. You may again pause the video to think of the answers yourself. Okay, I'm going to go through a motorist approach a traffic light junction at 54 kilometers per hour. The traffic light turns red when he is 30 meters from the junction. If he takes 0.4 seconds before applying the brake, so the 0.4 seconds is his reaction time. So he sees the traffic light turn red. He need to think a little bit, his brain need to process a little bit before, or his leg need to take some time before his leg step on the brake. Okay, so that is his thinking time. And then 0.4 seconds later, he will step on the brake and his car starts to slow down at a rate of 3.75 meters per second square. So you know meters per second square means it's an acceleration. In this case, it's slowing down, so it's deceleration of 3.75. Okay, determine whether the motorist can stop his car in time. Okay, so the keyword is in order to stop, he needs to stop within 30 meters. 30 meters is a distance, means I need to plot or sketch a velocity time graph in order to be able to calculate the area under the graph for the distance that he moved. Okay, so some of the assumption is that the car is moving at 54 kilometers per hour all the way until he applies the brake, never slow down. And then when he applies the brake, the deceleration is always constant at 3.75 meters per second square. Okay, so the first step, sketch a graph. Your graph should look like this. Okay, so there is kilometers per hour, but I don't like because when I sub into my formulas, I can't use kilometers per hour. I need to use meters per second. So the first part, they do a conversion over here. 54 kilometers per 1 hour is 3,600 seconds. You get 15 meters per second. So my car is moving at 15 meters per second for 0.4 seconds. So I sketch a velocity time graph. So the velocity is 15 for 0.4 seconds. After 0.4 seconds, I start to step on the brake and I start to slow down uniformly. Okay, so I see a straight line slow down until I stop, come to a stop. And the gradient of this graph is the acceleration. The gradient will be 3.75. Okay, so I sketch my velocity time graph first. Okay, so step 2, okay, I need to find the area under the graph. But before I find the area under the graph, I need to find how long did it take before he stopped. So I need to make use of 3.75, which is the acceleration or deceleration. Okay, so this gradient is actually equivalent to minus 3.75. So how do I sub in? Okay, I use the formula A equals to V minus U over T. Okay, let me just jot down here. A equals to V minus U over T. So I'm slowing down, so my acceleration is negative 3.75. My final velocity when I slow down is 0. My starting velocity is 15 over the time. So if I were to solve for my time, I'll get my time is 4 seconds. Okay, in order to slow down. Okay, so if I were to go back into this graph, Okay, this additional time is 4 seconds, so this will be 4.4 seconds because I start only at 0.4 seconds. Okay, so I want to find that the total distance that I covered after I see the traffic light. How much is this distance? If this distance is more than 30 meters, then sorry, I cannot stop in time. If it's shorter than 30 meters, then means yes, because the traffic light is 30 meters away. Okay, so I need to find this area. This is a trapezium. Again, half times sum of parallel sides. Parallel sides is 0.4 plus 4.4 times the height, 15. Okay, so I get area of trapezium half times 0.4 plus 4.4 times 15 is 36 meters. But my traffic light is only 30 meters ahead of me. So the answer is no. The car won't be able to stop in time because it will need a stopping distance of 36 meters. He will travel 36 meters to stop. Okay, so he will have overshot the traffic light. Okay, you may scan the following QR code to practice more about this. Okay, there is a lot of QR codes over here. Okay,